Steves.
So let's talk about, what was the last couple things you or a family member broke?
Well, yeah, I mean, last week my son broke his, chest of drawers in their room, and it was in a really weird way. Yeah, that was kind of annoying.
I think
So,
one of mine was a fishing net,
oh,
and my daughter wanted to catch butterflies with it. I'm like, I mean, you could try it. It's definitely not designed to be used to catch butterflies, but I let her use it, and sure enough, like the net she tripped on, it tore the little strings on there holding the net together. Simple
oh,
fix. I was able to retie it, so it's just
mm-hmm.
one little failure there.
It's kind of like a fairy tale type story. It's like my daughter tore a net while trying to capture butterflies. It's beautiful. It's springtime. I mean, up in the Pacific Northwest, it's
It
probably
is.
gorgeous right now.
It is. We got some overcast today.
Okay.
Yeah. So it's cooling down a little bit, but sure enough, I think the sun will come back. It'll be nice.
Yeah, down here in
You're
Los
in LA.
Angeles. Yeah, it's been warm. We've had some overcast days. I can see the little bit of the June gloom might come, which I welcome the June gloom. I love it. It means I could ride my bike outside like a little longer and a little like, earlier in the day. Because when it's 80, 90 degrees, I can't ride my bike. I get too hot. I get so tired. What's another word for being tired? Oh, like I get
Oh,
fatigued.
like you're fatigued.
Yeah, that.
It is the French word for tired.
Is that right?
That's right.
Oh, I didn't know that. I don't
At least
speak
that's what Google
French.
Translate told me.
Google Translate obviously rules the world when it comes to words. So I use it all the time. Yeah, that's French for tired. That makes sense. Okay.
But you got to be more durable and overcome that fatigue.
Yes. Yeah. It's not just being strong, it's being more durable, right? There's a difference there.
Because
Hmm.
you want a good fatigue life. You don't want a fatigued life. You want a good fatigue life. No, so that's interesting. So like, talking about fatigue. And we're live right now, so welcome to kind of like the pre-show, I guess. But, put in the chat, well, what was, when you think of fatigue and fatigue failure, what was the first thing that comes to mind? Like, do you have an iconic, like, oh, fatigue failure? Andrew, do you have one?
Fatigue failure, what comes to mind, it's just maybe this is just a product of going to school, but I always think of a connecting rod and an engine. It's like a classic fatigue life story, right? I mean, like you make a connecting rod that doesn't reach, quote unquote infinite life. Yeah. You have to be under that line, right? As that SN curve starts flattening out, you got to be below the line as it flattens, right? So that's for me. So it's always the connecting rod of an engine. What about you, Michael?
I think there's the classic story. That's just also a story of resonance and frequency. Is near where I live, the Tacoma Narrows Bridge.
Yes. You mean the overused example, the Tacoma Narrows Bridge?
It's like,
I mean,
actually, in the engineering community, where are you from? You know where the Tacoma Narrows Bridge is? I'm around there.
oh, that is awesome. It's a landmark of the engineering community. That's really cool because you talk to someone who's not kind of in our circle and they're like, wait, what? It's a bridge? You're like, you don't understand the inside information here from those
You
of
know,
us.
wasn't on the cover of some of your engineering books? No.
Okay, so we have hit the top of the hour. All right, my name is Andrew Gross, and I want to welcome this new version, this latest episode of SolidWorks Live Design. So I'll be hosting today. Really excited about this, and as my guest, I'm having Michael Steves. Now, let me read here. This is what he's proposing to do a presentation on: recognizing fatigue and how to fight it. So I got a little blindsided here, everybody. I didn't realize that Michael Steves was going to be basically, this is his soft open for his self-help book.
Yeah.
So Michael, would you like to talk about this book that you're writing, Recognizing Fatigue and How to Fight It?
No, I think it's going to be something to not only help your personal life, but also the life of your products. So maybe we do kind of a balance with this, right? We can
harmonizing.
Is there too much stress in your life, Andrew? Are you feeling
Yes,
tired or fatigued?
I am.
Do you feel
I
like you're doing the same thing over and over and over again?
That's great. I do. These are. I mean, this is real. So far I'm really identifying with what you're with the title of this of the SolidWorks Live Design presentation that you're doing today.
It was actually pretty fun creating the thumbnail for today's session because it's like, how do I combine both of these worlds of fatigue in the engineering and design
Uh-huh.
realm, as well as like real world realm of individuals like you and me and our audience and how they may become fatigued.
Yes. Yeah. Well, I mean, that's a big deal these days. A lot of us working from home for the last year. My kids schooling from home for the last year. Yeah, lots of fatigue in this house.
So, but is a good diet, is water, is a good amount of sleep, what's the correct regimen for your product, for your designs.
Yeah.
Now, if you have a
Yeah.
product that, it has a longer life from those things, that would be really interesting to see.
I can't wait to see. So, Michael, what do you have? So, what do you really have in store for us as a presentation today?
All right, so like you may have seen in the thumbnail, we're going to be taking a look at a chair, and I've got it up here on screen.
Hmm.
It's a fictional chair. Helios is the name of this chair. It's designed by actually many different design tools went into what you're seeing here, from CATIA to SolidWorks. And when I say SolidWorks, I'm talking about SolidWorks Desktop as well as some of our web applications. 3D Creator, 3D Sculptor, and the apps included in those that build these 3D models. So what we're taking a look at is kind of a multi-CAD assembly coming from a variety of sources. I'm just going to take a look at the underside of this chair, and I'm sure you and I, Andrew, we're both standing. Why are we standing? Did we both break our chairs?
Well,
Like,
yeah. Maybe I got sitting fatigue is what happened at some point. Yeah. I went from a I have a really nice chair, but at some point I moved to a standing desk. Because sometimes I would get a little too fatigued in that chair sitting. But yes, this is the chair that I use looks very similar to this, or that I used to use, honestly.
so there's many components in here, and actually, I was talking to some other colleagues. It's like I don't think I've ever broken a chair, and I was challenged back. It's like, no, you haven't broken a chair before. Like, it's like maybe I don't use the same chair long enough to kind of hit that finite life that a chair may have. I'd be interested. Anyone in the chat failed a chair? Let us know.
Yeah, we want to know the aftermath of that as well. So you failed the
Well,
chair, but then what?
see, the fail I
Then
usually
what?
see is like you're leaning back too far and the bottom of the chair just goes right out from under you. The
Hmm.
chair's okay. You might be banged up a little bit, but you can get back into place. The chair may not be totally failed. So that's what we're going to take a look at with this Helios chair, is taking a look at some components. Not everything. We don't have enough time for that today. But take a look at some of these components and take a look at some of the stresses that are there, some of the strains, and use that information to get some feedback on what is the life, how many cycles, how many times can a person sit down in this chair or lean back or put their load on the arms of this chair. So before I get, hang on to that thought for just a moment. I want to just show you here some of those components that we're going to focus on today. We have the orange arms of the chair. That's one of the components that we're going to do there. And one thing that's unique about this chair, it's kind of interesting. The back of the chair is actually attached to those arms. So that back is kind of floating. Really cool design. But then those arms obviously mount to this sheet metal mount that is fastened to the bottom of the chair. So those arms were modeled with X Design, one of the X Shape, the freeform subdivisional modeling tool on the cloud, and the sheet metal part was designed in SolidWorks. Look at that! How cool is that? Take a look at the flat pattern there. Now we're going to come back to this sheet metal part towards the end of today's session. And because we're going to focus on that arm, we want to make sure we have a good solid arm, but that may not be the total picture. I mean, if you're designing products, you're designing maybe one part at a time and trying to figure out, well, how strong is this part? Will it work? We really need to take a look at the bigger picture of how components are connected, and then what's the weakest link. And that's where and I'm gonna spoil it here, Andrew.
Oh no, no, not spoilers. I hate spoilers.
The sheet metal part is the weakest link.
Oh, dang.
So
I just put $1,000 on the arms, so it's over.
So as you take a look at this, it's like, I'm curious if anyone in the chat, if anything stands out to you, why do you think that the sheet metal part is the weakest link? We'll take a closer look at why and talk about what things we can do to improve it. Okay, so I've been on SOLIDWORKS Live Design before. Back in episode 2, I did a structural analysis of the shredder. We've seen the shredder, right?
Oh, I've seen the shredder.
Seen the shredder, kind of that skateboard attached to a ride-on tank.
Yeah, it's such a crazy device. Looks pretty fun to ride though.
Okay, so I'm gonna throw back to a couple things there. So if you haven't seen that episode, feel free to go back and watch it. But I'm gonna do a couple things again, and we're gonna do it a little bit differently, specifically when it comes time to setting up the models. To perform an analysis, because there's a couple different challenges that come up here working with this chair. All right, so the first thing we're going to take a look at that we're really going to focus on and kind of hammer home is the design of this arm. This is the first component we're going to focus on. And let me just load up some of the results here for this arm, so you can kind of see what's going on and understand kind of where this load path is going through and how this is loaded up. So I have an analysis of just the arm only. And what we're doing here, if I take a look at the side view, we're actually applying a force to where it's attached to the back of the chair and pushing that out at about 200 pounds. So if you look up a lot of chairs, a lot of them were rated for like 400 pounds, right, for you to sit in. So this is kind of the case where if you're sitting in your chair, you're leaning back, and like worst case scenario, all of your weight is like going right to the back of this chair.
Mm-hmm. Yeah, I mean, what an interesting design where the arms kind of are dual function here, right? Where they not only are armrests, but also basically connect the base to the back. So much load going on there. So we have a couple questions in the chat real quick, and I hope that we'll answer them soon. Yeah, not yet. So Rajat Gupta, he's asking about mesh quality. So I'm imagining, Michael Steves, we'll get to that at some point. Is that correct?
We are definitely going to get to that. So let's take a look at what went into setting up this study, because remember, we're going to be talking about fatigue and durability, but we're not there yet. There's a couple prerequisites that we need to have when we talk about fatigue and durability. Any guesses what they are? I mean, chat, feel free to pop up what you think what kind of prerequisites, what kind of information do we need to do a fatigue analysis? Oh, we probably need a model. We've talked about the chair already.
Okay.
Right, so we've got some geometry. But what's going on with that geometry? We need some sort of structural load that's going to give us the stress.
That's right. So, we start with stress, right? Don't we have to start with stress? Yeah. If I remember right from school years ago, right, you always start with a stress calculation when you want to calculate fatigue, right?
Yep. So we have this fatigue curve. So that kind of gets into the material properties.
Mm-hmm.
So we'll talk about material properties.
Oh, Sumit Sonawayne, sorry for mispronouncing your name if so. Number of cycles.
Yes.
Right? We want to know that. That's a good one.
Yep.
A valid static analysis from Sujay Desai. Absolutely. Got to be a valid static analysis. Yep.
So we've got material, we've got our load, we have our cycles. And there's a couple ways that we can do the cycles. We'll explore this a little bit as we look at these different scenarios. But overall, it's like kind of for this initial load case that we're talking about of this load applied to the back only, how many cycles can that go through before we hit failure? And one thing to just remember here about kind of the fatigue approach is it's statistical, right? I mean, in terms of calculating that curve and comparing that to, physical tests, it's a scatter plot almost, but there are these general curves that we can use and apply, conservative methods to reasonably predict the life of the design.
Right.
So,
I mean, an SN curve, we've all seen those SN curves. It is a scatter of points, right? And it's all tested empirically, which I think is one of the coolest things. They have these rooms filled with materials spinning on those rotary machines and just checking for failure after a certain number of revolutions based on stress, right? Isn't that how they calculate the SN curve?
Right. So keep going there a little bit, because depending on the type of material, they can have, obviously different behaviors, right? With steels, you usually have a very good estimate on what that infinite life is. But for things like aluminum or other materials, may not be the case. So, how we approximate this and how we automate these calculations, there are a variety of different fatigue methods and algorithms that are used. And actually, those are built into, the software that we're using today with Simulia. I mean, and what we're leveraging here, the underlying technology is Abacus, leader in structural analysis, and also FE Safe, which has also been around for a long time, a leader in durability in fatigue analysis. So with that, I mean, with this solution, materials are provided that have those simulation properties already defined. So let's just I don't want to just go through a variety of menus here. We want to get back into how that study was set up. But I do want to make sure that, you understand that when we take a look at, the multi-physics that Abacus addresses here, we're going to focus on some of these durability properties. And, looking at this without going through training, and by the way, there's some fantastic training on the EDU space for 3DS. You can also work with your local SOLIDWORKS reseller to get training on this. But as we take a look at what's being called out here, for the fatigue algorithm that's being used here, where you can actually do low cycle fatigue, LCF, high cycle fatigue. For this model, it's strain based, can be used, in addition to stress. There's also this really interesting one, and again, I'm just going to keep this at high level here, but CP. Any guesses on what CP means?
Yeah, if you know what CP means, if you have a guess for it, hit it up in the chat. We'd love to see what you had to think.
Okay,
I have a guess.
Some of the first times I was using, simulation, SolidWorks simulation, doing a fatigue analysis, I wasn't leveraging it here or there. We're leveraging it here, though.
I have a guess.
What's your guess?
I mean, I'm guessing it's creep.
It is not.
It's not creep.
Critical plane.
Critical plane. Okay.
Right. So as you have, if you have your different stress components.
Okay.
What is the critical plane in that area that's going to result in failure for fatigue? So what happens automatically when we apply this fatigue algorithm, this critical plane, it's doing a search. It's automatically rotating to find the different planes that it'll solve and find that worst case scenario, that critical pain. And that's what's also being influenced for that fatigue calculation. So there's a lot of knowledge that's built into the software. So there you can see a variety of the different algorithms that are available that can be used. One thing that's really nice, though, is, like me, it's like, hey, this is the kind of steel or aluminum that I'm using. I may not necessarily know what algorithm I want to use with the materials that are built in. Those are already selected for you. However, if you are, with this environment, you can create custom materials. And if you have either from other literature or if you have, results from your own physical testing, you can, select the appropriate algorithm, and you can go through here. So there's a couple other properties here, and some of these may be familiar to, some of those old, hand calculations for fatigue, for like the cyclic stress strain. What's the endurance limit that you want to apply here, so that once it hits that point, that's what essentially we're calling infinite life. Our components for the strain life calculation, what's our proof stress or our yield stress, and what's the ultimate strength there. So that's where there are specific properties that we're leveraging here when we do the durability calculation. Also that fatigue algorithm, very powerful stuff. And when we take a look at different materials that we can use, one thing that you may want to do here, browsing through here, is compare different materials and see which one may be stronger. So here we're just looking at the 1038s here, from one that's been quenched. And we can see the difference in Young's modulus there and the yield stress. So in this case, the normal one is less expensive, less processing that's going into that material. That's one that we're going to be using today. But keep in mind, there are hundreds of materials built in. I've even imported a couple libraries, as you can see here, aluminum and aluminium. For
that extra, the British eye, right? Right. The added additional eye. Well, I just want to say about that compare materials, Michael Steves, I'm sure people in the chat, if you've ever done this, because I know I have you ever looked at multiple materials, whether you're searching in Google or whatnot, and you're sitting there writing down the name of the material and the elastic modulus, and then you start writing down all these ones, you compare it that way because you're just looking at all of the stuff online. That compare materials is such a great way. You can just really just see what material properties are going to be great for your application. I love that.
Yeah. Okay, let's take a look here. So I've really filtered this down to just the one component of interest. And I've shown this before, but visualization management really makes it easy to just show what is contributing to the selected analysis or this scenario of interest. And over here, you can see that I've got a variety of studies that I've already set up and solved. And we'll take a look at these just to kind of fast forward here, so we don't have to wait for different solves to go on here. But let's take a look at how this one was set up. So let's go ahead and turn on kind of what's going on here. So we have a couple hinges defined, for those bolts and how that's mounted to that sheet metal component that we saw earlier. So it's just able to rotate around those just like, as a loose fitting bolt would, but it's not allowed to translate along that axis. Also, because we're only solving one side, I've set up a fixed displacement in the Y direction there to constrain it from moving side to side. Because again, we're assuming symmetry here, cut in half. We have that back that's kind of holding it in that Y direction on screen. And then for our loads, we just have that 200-pound force. And one thing that's nice here, we see this in SOLIDWORKS a lot. So if you type in a specific value, you can put in the units, automatically converts it over there for newtons, which is the unit default here for this study. So that's it for kind of the setup here. We talked about the material, and then one thing that's important is the material that's specified here it does have those fatigue properties. Because what's going to come up here in a second is when we do that durability analysis, we need that material to have those properties. Okay, there was a question on mesh. Let's take a look at the mesh that was used. And we'll just show what's contributing to this mesh. As you can see, it's very fine. And I even have the quality turned on there. You can see all those green elements. Green is good. Let's hide the shape. And this is a best practice. I mean, when you're doing a fatigue analysis, and by the way, I think I've shown this before, but if we take a look at our mesh tools, we do have a quality analysis tool here that just kind of automatically bulks everything together and says, hey, I actually only have 3 elements that are poor regarding their stretch component. Everything else is pretty good. So I'm not going to, when we get to that sheet metal component later, we're going to dive deeper into meshing. But I just want to say what I've done here, because mesh is important. We want to make sure, one of the best tips when you do a durability analysis is that you have a converged mesh.
Converged mesh. What does that mean?
Converged mesh. I know, that was the first time I heard converged mesh was when I was getting familiar with SOLIDWORKS flow simulation, doing some CFD analysis, right? It's like when you're areas of interest, you set these engineering goals and parameters. Like in this case, is it maximum stress, for instance? You run the study once, you take note, you can use like trend tracker or other sensors and parameters to keep track of these things in the software, or pen and paper could work okay, I guess. But you can, you take a look at these engineering goals. What are the things that you're after about solving? And you then refine the mesh, solve again, and compare that parameter. Is it higher, lower? How did it change? And a converged mesh will result in that same value. So that's what we mean by converged mesh. So that's a top tip there when we do a durability analysis, is make sure that you have a converged mesh. So like what I have here for this study. So we took a look at some of the results earlier, specifically the stress that's going on there. And let me actually just pop back in there, because there's one. We're going to use that information to set up a durability analysis. But I want to kind of get your take on this, Andrew. As we take a look at some of these sensors here, I can show. We should be able to take a look here for, that was the different arm only. This is the one. Yeah. So our maximum stress, von Mises stress, mind you, is right there.
Okay.
And I think, thinking about this further, I think that might actually be our failure mode. Spoiler alert, I've seen the durability study already. So you can see, and one other thing regarding durability, as a result of that fixture that I applied in the Y direction, we do have, in this case, I would call artificial stress. So that's one other thing to keep in mind, depending on the quality of your simulation study or that structural analysis. You may have some stresses that are, hotspots that isn't necessarily real stress, and those can be areas that would be ignored when interpreting, obviously the structural analysis like this, as well as the durability results. So let's actually set up a durability study from scratch. I already have one created. We'll switch over that to take a look at the results here, but let me show you what it looks like to set this durability study up.
So one second, Michael Steves.
Okay.
There's another question from Sujay Desai. I like this question a lot. So you've already established a mesh independency of the solution. So what do you mean by converged mesh? So maybe he didn't get the full explanation. So maybe I can answer. Like we used to call that a mesh sensitivity study. I don't know if people use that term anymore, but if that that would answer his question a little bit. But maybe go a little bit deeper into converged mesh, just real quick.
Okay, so and maybe I can. Yeah, what I would do, I think of it as a process. Maybe you create a study. Let's show the current mesh. And you have parameters for the mesh that you've defined, like the mesh size, for instance. And normally, it could be pretty coarse. I think that the default mesh size for this is about 7 millimeters. So we would run the study at that coarser size. You would take note of the results. When you're processing the results, you take a look at, okay, what is the maximum stress? You could take a look at the contour plot. Once you've taken note of that, you then refine your mesh. And what I mean by that is, like in this case, I reduced the mesh size, in this case, to 3 millimeters. And actually, before this, going through this, I reduced it from 4, ran the study, set it to then 3, ran the study, and sure enough, between 4 and 3, that's where my mesh plot my stress plot wasn't changing, right? We were getting consistent results as we get finer and finer on the mesh. So that's where that's where I say a converged mesh, because what's changing there is the mesh size. We're getting smaller and smaller, taking a look at that maximum stress value. And that maximum stress value is what converged. So hopefully that's clear.
So Michael, I don't know if you can see this Oh, maybe it doesn't come through on the iPad, but I drew a little plot, right? That's
No,
kind of
you
what
got
we're
a
looking
plot.
for, right? We
Here's
have
our
like,
stress.
we have our stress up here, and then we have our, mesh density going this way, and hopefully we want it to flatten out at some point. And that tells us, yep, we've reached that convergence point.
So
Oh, there we
usually
go.
like with a smaller size mesh to the right, a bigger size mesh to the left, we would expect, with the stress value, yeah, it usually goes up, but it could change, but something that flattens out. So once we hit, this point here on the, once we've had consistent stress, once we, go smaller and smaller on that mesh size, that's what I mean by a converged mesh.
Great.
Hopefully it's crystal clear.
No, that's perfect. And Sujay just said, yes, exactly. I think we're just using different terminology. Thank you. Okay, so that was great.
Perfect.
So that's perfect. Thank you so much for going back and taking another look at that, Michael.
Okay, are we ready to create a durability study?
Heck yeah.
Yeah. Okay, so it's very similar to creating a structural analysis, but we have some other dedicated tools here. If you go back to that shredder analysis study that I did before, you come down here, you come to, setup. I can create a new structural analysis case here. But that's not what we're doing in this case. With this, we have a dedicated durability tab. This gives you the tools necessary to define, set up these parameters for a durability study. So here we have creating a load case for durability there. And similar, we can duplicate an analysis case. So like if you've already put in some work to a durability study and you're like, okay, I want that and I want to keep it, but I want to do another one and reuse some of that work, you can duplicate it. Okay, durability, new, we gave it a name. The assistant on the right-hand side, I love using the assistants. It helps keep me on track, especially for new users here. It helps you go through all these different steps to be set up for success, a successful run of the analysis. Okay, let's take a look at fatigue loading as the assistant suggests here. So we get this structured tree. I'm not gonna explain everything here. We're gonna touch on some of these a little bit later on. But there is, global default temperature. There's this thing called inter-event transitions. I have an example that I'll show later. But to define this, we need to choose either a superposition or a sequence of frames. In this case, it's a very simple load case. We're going to choose superposition. I'll show you an example of sequence of frames later on. So with this, we can specify, right, the number of repeats, the scale if we want to modify that. The fields that we're using in this case, we're going to use stress. We'll talk about strain later on for that low cycle fatigue. So what we need to do next is, well, what is the frame? What is our reference study here that we're looking at? So I'll right click, choose add frame, and we'll choose that arm only back last increment. But as you can see there, I have all the other studies that are available for me that have already been set up. And one thing that's interesting here, you don't have to solve these studies ahead of time. You can solve, you can just set them up, and then you can solve both the structural and then the durability study when we're ready to solve. Okay, so that's the arm only that we want. We can, because you can apply multiple, oh, I picked the, it's meant to do superposition. Oh, I did. Delete. Add frame. Yep, that's what I want. So because you can add multiple frames here, so I can, to create, different types of load cases, we'll take a look at that later. That's why we can individually apply individual scales to those frames. So for a frame, we need to add a signal. Here, 0 to 1. So it's not fully reversed. The default value there was -1 to 1. That'd be like if we're, right, what would that mean? That would mean if we are not only leaning back in the chair, but then pulling the chair with you if you're leaning
like someone's
forward.
behind you pushing the chair or something.
Yeah, that's not necessarily the load case that we're after here. We're just in just leaning back in this chair, right? So 0 to 1. It's not loaded, it's loaded. So very basic here. The other parameter though for this that we want to be interested in is the surface finish, right? And there's a lot of scholarly articles on fatigue and kind of what that means and how it comes into play, right? So we're interested in the microstructure, all these little microscopic voids that are in the material, but also one of the big influencers there in terms of the life is the surface finish. So there is
I remember those K values.
Right, this KT value. So
yeah, and you have to multiply them all out, and all of a sudden, oh man, this thing can only last like 4 cycles.
If you know that K value, you can specify it. But what's also available here are other surface finish values. So if you're like, well, I know how it's going to be finished, so I can actually say, because this is a high quality chair, we want a mirror polish on it. So this actually has, that value associated, and applies this for us for that base surface finish. The other interesting thing here, I won't apply it here, but you can individually specify different surface finish values at different regions of the model. Let that sink in.
Wow.
Right, so if you know that a specific area in your model is, more inclined like to have a higher load or a higher stress value, it might make sense to add a finer polish or have a better surface finish at those areas to improve the life at that specific region.
This also can take into account certain manufacturing processes, right? Maybe lowering the cost of a part based on, not as great of a surface finish on like a more visible area, but then that could be critical in how it's going to fail.
It's like a cast part that also has machine surfaces on it.
Right.
Okay, but from there, I mean, that's about it. We're ready to run. So let me do this instead. We're going to take a look. I'm just going to toggle over here to the study that's already solved for us. And we'll take a look at the results. All right, results of our durability with our back loading. So by default, and sure enough, we get a little hotspot here. And what I can do is click on the plot, toggle on our min-max values. This is a handy tool. This pop-up menu is great. You click on the model, gives you some common tools if you want to do section clipping, if you want to hide show components, if you want to edit the plot. It's already there available for you. So let's toggle on our show min-max and show our minimum value only. So sure enough, it was there right in our highest value, but the value is 5. It's not 5 cycles. So the plot that we're looking at now is a log of life. So the plot that we're looking at is a log plot. So when we talk about a SN curve, like we were talking about earlier, usually it's a log plot, right? The number of cycles is in log form. So it stays in that consistency in that same format, which is handy if you're used to viewing the values in that way. But if you're not used to doing a lot of fatigue calculations or using some of these plots, a cycle plot may be of interest. And this is where we do get some flexibility with our post-processing with these simulation tools. And let's see if so what I can do here is actually create a field expression. So this is a unique tool. So in calculations down here, we have field expressions. What this is going to let me do is create my own custom parameter or my own name. So what I have here is cycles, and we define this as 10 to the power of the log life, which is going to give us the number of cycles. So there's no dimension here.
Now I'm starting to understand what that log of life value means. Interesting.
Yeah. Cool. So let's create a new plot here. We'll choose our cycles. And oh no, everything turned red.
Red bad. Red bad, right?
Red bad, right? Right. Double click on the plot there and turn on reverse colors.
Kind of like what you do with a safety factor plot, right? You always kind of want to flip the colors.
Exactly. Okay, so there we go. So sure enough, we have that hotspot there. And what our value is about 111,000 cycles. So that's interesting. I mean, how many times are you going to sit down in this chair? So just keep note of that value there. And maybe since we're going to be kind of default looking at the log plot, about 5.05, right? That's our estimated life there for this arm, for this loading. But there's more types of loading here. So this is where, you know, we have to go a little bit. It gets more complex with this complex loading. I mean, I think about back to some of those hand calculations, and you think about the rain flow counting method. You think about Miner's rule. You know, when you have different types of loading events, because the other loading event that we have here is a vertical load. So let me toggle back here over to our scenarios. We have a vertical load. Actually, you know what? I jumped the gun. Before I get to vertical load, I wanted to take a look at one other study. I set up a different, because the question I want to ask there, with that 111,000 cycles, is that low cycle fatigue or high cycle fatigue? Any guesses on which range we're in?
Yeah. Why don't you put a 1 in the chat if you think it's high cycle fatigue? Why don't you put a 2 in the chat if you think it's low cycle fatigue? I'm interested to know the answer to that too.
Okay, so what we're going to do to get a more accurate calculation is we're going to include strain in this calculation and see how it compares. Because we can account for both stress and strain. And you can turn off, you can have one on or have both on. So let's take a look at how this one was set up. So we did a similar durability study here. Let's just show our contributing components there. The loading here is a little bit different. So in order to account for low cycle fatigue, we do this as a sequence of frames. But when we set this up and we choose our frame, you actually have the option to choose all increments except the first. The second option is very helpful if you're setting up multiple load cases that may happen sequentially or that you want to tie together, or have if you're working with residual stress, which is also an important thing to include, or just the last increment. So that's what I chose, last increment, to have something set up like we did in this first durability study. But what I can do here now is include both stress and strain in this calculation. And the automation really kicks in here. And the other thing I want to mention here is, we may be getting into the plasticity range of the material. Earlier when we just did stress, what was automatically done there is automatic plasticity correction was built in. But depending on the material model that we're using, when we include strain, it's kind of kicking up the accuracy there and basing that calculation off of strain as well. Okay, so otherwise than that, we have scale options if we want, but we don't need to use that here. One thing that's different is we don't have our signal, because our signal here is just looking at what's that sequence that we're doing here, and from zero stress to that maximum load of the stress. So that's how this one was set up.
So look like we got some results in the chat, Michael.
Okay.
And
so what do you think?
So I agree with the chat. 111,000 cycles, everyone thinks is high cycle fatigue. I agree with that. What are your thoughts?
Well, let's see.
It's right on that border, but I do think it's on the high cycle side. Let's see.
All right, so let's take a look at our results when we did both. When we did both stress and strain. Log of life, we actually have more life that's being calculated here. So we were at 5.05 before, now we're at 5.32. So that means for when we just did stress, that was giving us a more conservative value. Now, granted, this stress strain calculations does result in increased data and takes a little bit longer to solve, not much longer at all. But yeah, we are able to include that strain component to get a more accurate result. So even if you are in that low cycle range, or even around in those transition areas, again, depending on the material, depending on the fatigue algorithm that's being defined for that, including both, increases our accuracy there.
Interesting. That's cool.
Okay, so now let's take a look at the other type of loading condition. So everything that we've seen in terms of results so far is just that back load. You're leaning back in your chair. All right, well, how about you're either getting up out of your chair, or you're maybe repositioning yourself. So you're putting your arms onto the arms of the chair to lift up, and you're applying, the weight of you to those arms. So now let's bring that into the equation. So similarly, I set up an additional structural analysis case of a vertical load. So we'll toggle there. Let's show what is contributing. Hide our mesh. There we go. So similar restraints. The only difference here is this loading at the top. So what I defined here is, in this case, 200 newtons going down as you're lifting up. So how does that influence our values? Because similarly, we can get our stresses and we can get our durability. Before we jump over to results, I'm going to show you what we did in the durability study, because this is where it gets a little bit more interesting in some of the calculations that are being done. So for our back and vertical. So I used superposition here. And for, let's see, this is our back only here. And here's our vertical. They both have a 0 to 1 signal. But what I said here is that the leaning back, you're going to do twice as often than you are repositioning yourself, putting your load down on the arms. So that's where you can use these repeats and values to control how often something is happening. Alternatively, if you do know how many cycles you want for each of these, you can plug those values in. And then we can interpret the durability results a little bit differently to see how much life has been consumed or how much damage has been done here. But in this case, with this approach, we're taking a look at, okay, what is our calculated life for that arm?
Okay, so Michael, we're assuming that twice as often you're leaning back versus using the arms to get out of the chair to, say, get a cup of coffee.
Yeah.
Okay, because I mean, I only drink like 6 or 7 cups of coffee a day. I probably lean back. No, I'm kidding. I probably lean back at least 12 times a day. I like it.
So here's what's interesting. We've actually, if we take a look at our log of life now, we're at our minimum value there is 4.75. So as you can see, I mean, it's critical that we account for these various load cases and how they combine. Oh, one thing I did not mention here is, let me toggle back there just to show you where this option was, because this is an interesting option. I think this is a great application for this fatigue loading. All right, so for our back and vertical load here, this option here, inter-event transitions. If I turned that off, what we're saying is that the loading on the arms and the leaning back is completely separate. But I left it on, and I left it on for a reason. I mean, as I was sitting in my chair thinking about this and leaning back and adjusting myself, I'm like, oh, I did it, right? The loading condition of me leaning back, applying that load on the arms, and adjusting myself, putting my load down, lifting myself up off the chair a little bit. Like I could go from that stress state of the back load to the stress state of the load on the arms. And if you're thinking, the difference in stress there throughout the entire model, that's with the inter-event transitions, that's how it's capturing that change in stress. Otherwise, with inter-event transitions off, it's not accounting for the transition or the stress range that can occur between those different events.
So you're assuming completely isolated events with it off.
Yeah, inter-event
Two things
ties
them together. Cool.
Ties them together. Okay, so we got our kind of understanding of our arm, but we've got about 15 minutes left here. Let's take a look at what this means for more of the components of the chair. So what I did here is we set up a separate analysis case, and there's something really cool here I really want to show in terms of what was unique for that sheet metal component. We saw it inside SOLIDWORKS earlier. Let's just toggle over here because this is the modeled part, and this has been inserted into this model again using I think CATIA is the master model here for this chair. But so there's some X design, some X shape that we talked about earlier, and this sheet metal component is from SOLIDWORKS. Easily be inserted, used, and referenced, and definitely included in the analysis here. But as you can see here, Andrew, it looks a little bit different.
Sure does.
It's simplified. One thing I'm tired of is having to make things simple. But some of the tools here, I do it a lot. I try to make things as simple as possible. And I have a lot of repeats of that activity. I don't necessarily know if I'm getting tired of it because there's some powerful tools here that make it easy. So let me actually show you what that process looked like for this model. So for the seats, we would take a look and dive into the structure of this chair. I'm just going to open up our chair in its own app there, because there's some things that are kind of unique here that are going on. I have a separate analysis. That's why you can see kind of this full mesh that's available throughout. Actually, I'm just going to take a quick moment here and pause. I'm going to toggle back to SOLIDWORKS here because you may be wondering, it's like this is one of the big benefits of using PDM, using 3D experience like we are here, is taking a look at references and where used. Right? It's like this sheet metal part, where is it used throughout our company? We can take a look right inside SOLIDWORKS and see that sure enough, it has some parents. It's used in places, and it's actually used in 2 simulations. So I do have a separate simulation of just that sheet metal bracket all by itself. And of course, there's the Helio simulation that we're working on now. So really cool to kind of see where that's used. But since it's used in multiple simulations, it has multiple meshes or finite element meshes. So that's why we're seeing that over here. So to keep this unique and kind of cut it in half, what I've done is an abstraction shape. And I talked about back when I did the shredder in episode 2, how to create the abstraction shape and how this references the source model from SOLIDWORKS. So this inserted solid model here, notice how we have this green thumbs up. That's letting me know that it's accurately up to date to the body, that's body 2 from SOLIDWORKS. So with that body, let's go ahead and hide this for a moment. Oh, that's the one that we want. Let's hide. There we go. So and let's hide the mesh. There we go. So there is the same body that we had inside SOLIDWORKS, but it's a linked copy. What I did next is I created a mid-surface. And this is really cool. what we can do is set this creation mode to mid-surface, because there are idealized features here down at the bottom where we can create this mid-surface. This dialog pops up. We choose automatic. It automatically, finds the thickness and inserts. And now I can show it. Inserts, we can see this edge that's now in the thickness of the model.
Oh, wow. So
right?
even if your sheet metal part, or if this part had multiple thicknesses throughout, like maybe it was a composite part, it could calculate that mid surface as well, even if there were different thicknesses along the part.
So throughout if there are, yes. So if
Cool.
it is varying, it finds it throughout the model, does it automatically. And since we're doing symmetry here, I did one other thing. I used the split command, which is also down there in Idealize. You could trim, you could split, where I used that symmetry plane to just kind of cut it in half, very similar to some of the tools that we have in SolidWorks, to give us half of the model of interest. So this is, eliminating a lot of complexity, and it's going to help us with our solve time while still maintaining a good quality result. Because again, that conversation of mesh really comes back into play. So let me toggle over here and talk about the meshing of this component a little bit, because there's some also, we have some fixtures around the holes, or we have these bolts that are tying this into the seat. We have the bolts that are connecting from the arm into this bracket. So how well are we doing on our mesh here? Let's show what's contributing here. So there's our mesh, and a couple things may pop out to you here. It's like, whoa, look at that. There's some nice refinement going on here in the areas of those holes. So we have these radiating elements going out from those holes automatically. That's even happening over in this area as well, which is important to make sure that we have good flow transfer, especially with those virtual bolts. But notice there's another hole here, but it is not refined. So there's some really cool meshing capabilities here that we're leveraging. So let's take a look at what I did there. With this surface quad mesh that was used, and there's a variety of meshes that are available. By no means is this an exhaustive presentation on the different types of meshes that are available here. But this was a very good option here. We can specify our default, or our global mesh size, 2 millimeters in this case. But then there's this capability under local specifications, or excuse me, where we're going here. We're going to go to edit all parameters. That's the one of interest, because in here we can set features for 2D holes, and that's one thing I've specified here. It's so automatically it's looking for maximum diameter of 6.5. So any hole that is smaller than this, what it's going to do is fill it with 16 edges in that hole. And what I picked here was 3 layers, and I can specify the size of each layer. So with this rules-based approach, it's automatically refining the areas of interest. Saves a lot of time for there. The other area that I've done is with the fillets. So with a maximum radius there of 3 millimeters, specified four layers there in those regions, and it, in this case, refined the mesh along this big, a lot of these bends here to make sure that we have good quality mesh, again, in those areas of interest. And that saves a lot of time. I know I've spent, when I'm trying to create a good mesh, Andrew, like I'm sure like you have, is going in, selecting faces, selecting geometry, and refining those areas of interest. Here with this rules-based approach, it saves a lot of time.
Yeah, it's great. I mean, yeah, how many hours have you spent in your life clicking on edges and small faces and refining the mesh locally? I mean, if you have a good idea and a plan of where you want the mesh to go and where you want to add more elements, this is such a cool way to kind of automate the process of refining things based on features and sizes of features. I love it.
Yeah, sure thing. Okay, so what was our loading here for this scenario? You can see some of the other boundary conditions that I set up there to tie some of these faces together with beam elements to how that's fastened to the chair. I'm not going to go in that here just for the sake of time, but I just wanted to review that we are looking at just the back load only, because this is like, we can definitely go through the same process with more components that we did earlier to take a look at what are our load cases and how we're combining all of those to get a good calculation of the life. But here it's important. What is the weakest link as you connect these different components together, right? So we're replacing a part on the new design. Okay, how well is that going to last? Oh, that lasted great because the same old part in the design broke. And that's, I alluded to it earlier. It's going to be the sheet metal bracket. But let's take a look. Let's take a look and see how it does. As this loads up here, just keep in mind that with that sheet metal, they're fastened together, but there can be some sliding that since that sheet metal is kind of folded over itself, it can come in contact with itself. So the other condition I set up there, and I did talk about this back in, I mentioned that shredder, live design that we did, because I talked about general contact there as well. It's definitely important here. So let me just play some of these results here, and you can definitely see, the maximum stress that's going on here is in that bracket. There's our weakest link. So, we can take a look at the stress. It is significantly high, and sure enough, it's in the locations of our fasteners. So maybe there's something that we want to do to better handle that. One thing that I also assumed here is that it is not coming in contact with the chair. So you can see it coming out of plane a lot there, Andrew. Mm-hmm. Right, that would butt into into the bottom of the chair and come in contact. I excluded that in this case, but just for the sake of time. But that's something if you really load this chair, when you lean back, is it going to rip those threads out from the bottom of the chair? So there's definitely more analysis work that we could do here.
But I think it's a worst case. Say you've used the chair for years. I would bet after a lot of years that it's usually a piece of wood that they use at the base of a chair. It could wear out, and all of a sudden you have a gap there, and then you're starting to see these types of stresses after years of use.
Yeah. So let's toggle over here to durability. Durability was set up in the same way, and sure enough, we can see here. Our weakest link by far is this is that sheet metal bracket. Remember the area of interest here on the arm? Infinite life. We're not hitting the stresses there. And that's why it's so critical to make sure that we're accounting for all the components of interest throughout the load path, especially of the components that we're designing. So, when at this point we're coming up to the hour, but we want to think about, how would we change this design inside SolidWorks for the better. So if you'd like to see more, make sure you leave a comment so we can see what kind of changes we can make in SolidWorks. Because again, the value here is we make a change in SolidWorks, that geometry is automatically propagated to these other apps on the 3D Experience platform for us to rerun the study and see these improvements made in the design. So that's kind of where we're at. Maybe, I need to get in contact with Debbie Designer. Is she the one that designed this sheet metal part? We got to see. So that's where, I need to share some of these results. And this is where we're going to wrap up, Andrew, is I need to communicate these results with other things. We talked a lot about fatigue today and durability. Hopefully I didn't make anyone else too tired over the topic. For fatigue.
Well, I've already finished my matcha. I think I need a refill.
Okay. All right. Very good. So, all right. This last part is like, personally, it's like, I'm tired of sending emails. Do I have to send another email? Since the results were created and stored on 3D Experience, we can actually access them from your web browser. So here, this is a 3D Experience dashboard for this chair. What we're taking a look there is that fatigue results, so we can have full 3D interpretation of this, and we can use this to mark it up.
Wait. Michael, what software are you using here?
This is I'm using Google Chrome.
Google Chrome? You're in a web
I'm in a
browser?
browser, in a web browser.
Oh my gosh.
So
That
maybe
is
we want
awesome.
to consider changing the positions of some of these components.
By the way, I'm very impressed with your mouse writing because mine never comes out legible.
Yes, I don't have a
That's really
touch
good.
screen. Oh yeah, so I could publish this image out. I could publish it to 3D Swim community, and this is where we see where the SolidWorks forum has recently moved to. We can save it out as a screenshot. We of course print it if we need to, but this is how we can communicate, with making these markups and communicate with the design team. So I can get in contact with Debbie Designer and work with her on how we can make some changes to the sheet metal bracket, maybe increase the thickness. But hopefully you guys have some ideas. Leave them in the comments and help drive this next stage of the Helios chair. All right, so as here, Andrew, what do you think? Are we ready to move on this next design and maybe a future episode or a future demo?
Absolutely. Absolutely. And you know what I love at the end, what you show is a lot of times FEA results, they're based on orders of magnitude differences, not small 10, 20% differences. If you look at the difference in stress or the fatigue life of that sheet metal part versus the arm, I mean, it is orders of magnitude different. And that I think that it's so cool to highlight that high stress region of the arm, the plot, we don't even see a discoloration there. We don't even see it even fading towards green or yellow or red. It's all in that sheet metal part. I love it. And so often this is the case, right? One piece that really is dictating the fatigue life of the entire assembly. Sorry, just had to put that in. I think it's really cool.
Thank you. Great way to wrap it up. Okay. All right. Well, that's what I wanted to cover with you. Thank you for having me back on Live Design. Just happy to share some of these new simulation results and get into topic of fatigue.
Awesome. Well, Michael, I want to thank you so much for joining me and presenting today. That was an amazing presentation. I absolutely loved it. I love fatigue. I love understanding how that changes, the performance of a product. So cool. Such great stuff. Thank you so much. And I also want to thank everyone who attended today, people who put all the great comments in the chat, and those of you who are watching, thank you so much for joining. If you liked what you saw today, hit the like button. Hit the subscribe button. We are doing these every 2 weeks. We are doing SolidWorks Live Design. Now, what's coming up in the future on May 13th? So May 20th is the next live. Mike Sandy, he was on just a couple weeks ago when he was talking about preparation for simulation in using geometry to prep for sim. But he's going to be talking a little bit about creating professional CAD renderings using SolidWorks Visualize Pro. So that's in 2 weeks, May 20th. Now, next week, Jeremy Regneris is going to be talking to Jason Poole of Orange County Choppers. Is going to talk to him on May 13th for SolidWorks Live. So make sure not to miss that. That's going to be really, really great. I will be very excited to see that as well. So once again, like or subscribe. Thank you so much for joining. Michael Steves, thank you again. And from SolidWorks Live Design, we're out. Thank you, guys.
Bye, everyone.
Have a great day.